EC201 lecture 4. So yesterday we saw that when we have a nonlinear network, we don't now have to be perturbed over the fact that we can't use any of our knowledge of linear systems, since after the initial tough step of finding the operating point, as long as the exciting signals are sufficiently small, you can reduce any nonlinear network into a linear network as far as those small signals are concerned. A couple of classes back we saw a simple example where we had just one diode and a resistor and one incremental source. Yesterday we saw a two-loop network with two independent sources and two small signals applied, and we saw that nothing any more complicated in a two-loop network than a single-loop network. The basic idea remains the same, and those of you who have a little more mathematical bent of mind can simply very straightforwardly extend it to an arbitrarily large network. So given any nonlinear network, if one is interested in predicting or analyzing the behavior for small signal excitations, what are the steps involved? What all should I do? First thing I should do is find the operating point. And what will this give me? Once I find the operating point, how am I better off than I was before? So once you find the operating point, you'll be able to find the quiescent voltage and current through all nonlinear devices. So find the operating point means this. And as I've been telling you, when you have a complicated network with many nonlinear devices, this is far from trivial. You can use a computer to do this job. So once all the quiescent voltages and currents have been figured out, you can find the incremental resistance of every nonlinear element. Alright? Once you find the incremental resistance, you can simply draw incremental equivalent circuit. And what do we know about the incremental equivalent network? This is a linear network. Use the techniques you have learnt in EMC or networks and systems to find or solve the incremental network, and once you have done this, you will also be in a position to find the total voltage or the total current at any node or through any branch. And how will you find the total voltage or total current? It is simply the quiescent value plus incremental. Does this make sense? So two more things have to be resolved. First, since we are going to be doing this over and over again, it makes sense to take a few very commonly used nonlinear devices and at least see what their incremental equivalents are, so that when you see this element, you can cut and paste the corresponding value of the linear resistance that needs to come into the incremental circuit. Does it make sense? That's one thing. The next thing, and perhaps a very important thing, is that we've still not really understood what this small signal means. To understand, everything here is predicated on the fact that the exciting signals or the incremental signals are so-called small signals. And as I've told you repeatedly, there is nothing small or large in the world. Everything small and large are only relative terms. So we need to understand what this small signal means. So before we do this, let's take a catalog of a few commonly used nonlinear elements and figure out what their incremental equivalent circuits are. The first thing is a voltage source. What are the characteristics of a voltage source? If I plot I versus the voltage across the voltage source, what will I get? I will get a straight line, this value being equal to VA. So is this a linear network element or a non-linear network element? Non-linear. Why? Why is it a non-linear network element? It's a linear element. If I double the current, the voltage would have doubled. Okay, so this is clearly a, since this doesn't pass through the origin, it is a nonlinear element. What would be the incremental equivalent circuit? What is the incremental network? When you try and find the incremental equivalent circuit, what are you trying to do? You are trying to find the incremental resistance of this two-terminal element, which is, you are trying to find the ratio of the change in current through the element due to a change in voltage or vice versa. Okay? So, here if I change the current incrementally by delta I, what happens to the change in the voltage? This is an ideal battery. So, the job of a battery is to hold the voltage across its two terminals to VA regardless of the current passing through the battery. So, if the current was I or the current was I plus delta I, the voltage remains the same. So, which basically means that delta V by delta I must be 0, which means that the incremental equivalent circuit is a short circuit. Alright. So, when you have a voltage source, a current source can't be far behind. So, what are the IV characteristics of a current source? Now, the easy thing is to plot the voltage on the x-axis, the current on the y-axis. It is constant, always equal to IA. So, the characteristic of a current source is that the current passing through the branch or through the source must be independent of the voltage across the source. Okay. So, now what do you find? So, what would be the incremental equivalent of a current source? It should be an open circuit because the change in the current due to a change in the voltage, okay, is 0, which means that the conductance or the incremental conductance of the current sources of an ideal current source is 0. Does that make sense? So, the incremental equivalent is an open circuit. What is the incremental equivalent of a linear resistor? Okay, if I plot I on this axis and the voltage on the y-axis, this is a linear resistor, so the slope of this is R, okay, which means delta V by delta I is R. So, in the incremental equivalent circuit, the resistor remains the same. Is this clear? The next thing, the semiconductor diode. This is the voltage, this is the current. Okay. So, if I plot V versus I, what happens? It's exponential in the forward biased region. And what is it in the reverse biased region? If the diode is sufficiently reverse biased, the current is a constant current. Okay, this is a poor diagram. There should be no discontinuity at the origin. So, let me just draw the curve first and mark the axis later. Okay. So, which is I and which is V? Y-axis is I or V? So, the y-axis is I, x-axis is. We have seen repeatedly that dV by di, delta I by delta V is I by Vt. Okay. Vt is kT by Q. I is the quiescent current. Okay. So, this is valid in which region of operation? Forward bias. So, in the forward bias region, the incremental equivalent of a semiconductor diode is a resistance of value Vt by I, where I is the quiescent current flowing through the diode. In the reverse bias region, what do you think it will be? Yes. What is it? It's an open circuit because the current through the diode is a constant. Do you understand? In the reverse bias region, the current flowing through the diode is constant and is equal to Is. If the current is constant, it means that regardless of the voltage across the diode, as long as it's reverse biased, the current is constant. So, a change in the voltage in the reverse bias region results in no change in the diode current. Hence, the conductance of the diode in the reverse bias region is delta I by delta V. Delta I is 0 since I is a constant in the reverse bias region, which means that the incremental equivalent of the diode in the reverse bias region is, it's an open circuit. Okay, let me take another example. Let's say we had a device whose characteristics were the following. This is a nonlinear device. So I is alpha times v square if v was greater than 0 and is 0 if v is, okay. In other words, if I plot v on the x-axis and I on the y-axis, it will be some kind of parabola like this, 0 on the. So what would be the incremental equivalent circuit of this type of element? V greater than or equal to 0, di by dv is nothing but 2 alpha v, okay. So this is the, what is it, resistance, or this is the conductance. So as far as the resistance is concerned, it's equivalent to a resistor of 1 over 2 alpha. So for v less than 0, what is the incremental equivalent? Di by dv is 0, which means is an open circuit, okay. Clearly in this case as well as in the case of the diode, you see that the incremental equivalent of the nonlinear element depends on the operating point, alright. From the discussion on the voltage and current source, we see that the incremental equivalent, does it depend on the operating point? Yes or no? No. So in general, the incremental conductance or resistance of a nonlinear element depends on the operating point, while it is possible to have special cases where this need not be true. Cases in point being the ideal voltage source and the ideal current source. Now what is the incremental equivalent of, what is the incremental equivalent? It's simply incrementally, okay. What about, you're tempted to say R, but it is actually, it's an open circuit, okay. What would happen if I replace the R by a diode? It will still be an open circuit. So the last thing we need to do is to figure out the following, which is, what is the small signal? So where is the approximation, what is the approximation that we have made here? In all our small signal arguments, what have we assumed? So what we have done is the following, okay. We have said that if you had a nonlinear element whose voltage was given by some f of x, if the current was I, the voltage was V, okay. If the current was I plus delta I, the voltage was V plus delta V, and we have approximated f of I plus delta I by f of I plus df by di times delta, okay. This is the only approximation in our entire framework up to this point. Do you follow? So we have approximated this as the following. This is only true is this approximation. So what is it in reality? What is it in reality? What is f of I plus delta I? F of I plus df by di times delta I plus 1 by 2 factorial d square I by di square times delta I square plus blah blah blah, okay. You understand? And we are approximating this entire series by just the first two terms, okay. So what is the error involved? What error have you made when you try to approximate something? It obviously implies that there is some error in your approximation. What is the error? This is the error, okay. So in other words, so now what do you think is the, in other words, delta V in reality has to be df by di times delta I plus 1/2 d square f by di square delta I the whole square plus 1 over 3 factorial d cube f by di cube times delta I the whole cube and so on. So this is the approximation. So this must be the, yes people, this is the approximation error, okay. So now can you tell me what small signal means? So what delta I would you call a small signal? Do you understand the question? So if delta I was obviously, if I made it infinitesimally small, then presumably the error is very small. As I go on increasing delta I, the error goes on increasing. Okay? So then how would you define small signal? Okay? So as long as the error, so small signal basically means that the error is much smaller than the approximation. So now the obvious question is what? What is much small? Right? Now this is now an individual's perspective. I might feel 0.1 is small. Okay. Some of you might feel 0.01 is small. Some of you might feel 10 power minus 5 is small. As long as you're consistent with definitions, okay, it's alright. Okay. So again, as I said, this much small being 0.1 or 0.01 or 0.001 depends on the application. In some applications you can tolerate some error, in some you cannot. Okay. So for uniformity, I don't know, let's just say 1% is sufficiently small. Okay. In other words, the error you made when you approximate this curve with a straight line having the same slope at that point, okay, as long as that error you have incurred is less than 1%, we say it is a small signal. Does it make sense? So small signal, this depends now on what all does this depend on? So we agree, let's say less than say 1%. What did we say? 1% qualifies. You understand? Okay. The notion of small signal now depends on what? It depends on the nature of f. Given f, one can find delta I, so that the error is equal to, okay, so given the functional nature of f, you can always go and find its derivatives, and once you find its derivatives, it's just a matter of you plugging in these formula into this equation, error equal to 0.01 times approximation, and find the maximum delta I allowable, which will keep the error within 1% of the approximation. Does it make sense? Okay. So the key point that I want to bring out here is that this notion of small signal is not an absolute notion. It depends on the functional nature of the nonlinear device. Okay. Alright. So let me quickly take an example. Let's go, let me take a voltage source again, ideal voltage source. What is the incremental equivalent circuit of the ideal voltage source? Pardon? It remains incrementally, it is a short circuit, and this remains a short circuit irrespective of the magnitude of current you pump into the voltage source. Okay. So even though this is a nonlinear device, any amount of signal qualifies as a small signal. Does it make sense? Okay. And that's because the I versus V characteristic has a straight line in it. It's just basically a straight line. Okay. So similarly, let me give you another example of a nonlinear element. Incrementally, this is what? This is RA. Okay. And what is a small signal? What is the definition of small signal for this nonlinear element? Pardon? Any current qualifies as a small signal because since the slope is constant, okay, the higher order terms in the Taylor series, they're all zero, which basically means that there is no error incurred in approximating the voltage for a current I plus delta I by simply the first two terms of the Taylor series. You understand? Okay. So now let me take a third example. This more numerical. You can plug in the numbers in the tutorial, but let me just draw something. So let's say I had two nonlinear devices, one which had I versus V like this, okay, and another device where the I versus V was like this, okay. Alright, at this operating point, so this is device A, this is device B, okay. So can you comment on the slope of the two curves at Ix? They look the same, okay. That basically means that the incremental resistance A, the slopes are the same. What does it mean? The incremental resistance of A is equal to the incremental resistance of B. Is it the same at all operating points, or is it only at I equals Ix? Does that make sense? Okay. Now, can you comment on the limit of small signal operation for device A versus device B? Does everybody see it, or is there a problem? Of course, you know, if you go and differentiate here, it may not be the same because the way I draw. But, okay, I think they look pretty much the same to me at least. You understand? So, the slope of device A is the same as the slope of device B only at I equal to Ix. Okay. Now can anybody make a comment on the limit of small signal operation for device A versus device B? So small signal for device B, I mean a larger signal will qualify as a small signal for device B when compared to a small signal for device A. And why is this so? You can see that the curvature of device A at Ix is much more than the curvature for device B at Ix, okay, alright. So, small signal operation, I mean for example if 5 millivolts is the limit of small signal operation for device B, okay, it will certainly not be small signal for device A because the characteristic of device A is changing much more rapidly, okay, around the operating point when compared to the characteristic for device B, okay. Now if I had a device C, so can you comment on the small signal, what would be a small signal for device C? Any signal would be small signal for device C, okay, because it's a straight. You understand? So the key point behind this discussion is the following, which is there is nothing which is absolutely small signal. The notion of small signal has to do with neglecting the higher order terms in the Taylor series, okay, when compared to the first term, and that obviously depends on the nature of the nonlinear. So 1 millivolt could be small signal in one application and could be very large signal in some other application. That's all I'm trying to say, depending on the device. Does it make sense? Great. Okay. So now, so far we've looked at networks formed with one-port nonlinear elements, right? So we have I is equal to f of v, and then you can make any network with such devices. Okay, you can mix and match resistors, resistors and voltage sources, current sources, and so on. Now you know how to evaluate the small signal quantities given any nonlinear network by first finding the operating point and then drawing the incremental equivalent circuit, solving the incremental equivalent network, and finding whatever else you want. Now, after the one port, in linear networks, what did you learn? A two-port network, right? So the next logical extension is what happens when you have a nonlinear, okay? So in a linear two-port what do you have in a linear one port? You need only one network, only one parameter to characterize the behavior of the entire network. Okay. So when you have an arbitrarily complex network, but you are only interested in the behavior between two ports, how many numbers do you need to characterize the network? We discussed this already. You need 4 parameters. So in other words, if you had a linear network, the voltage or current, for example, I1, V1, I2. So for example, if you chose I1 and I2 to be the dependent variables and V1 and V2 to be the independent variables, then I1 and I2 could be written as what? If you have a linear two-port network, I1 and I2 can be written as linear functions of V1 and V2. Okay. So if you have a nonlinear network, by extension, what can you say? So by extension, what can we say about I1 and I2 when the network is nonlinear? In a linear network, what would we say about I1? And if it's a linear function of V1 and V2, what do you understand by linear function? Now, by the same token, when you have a nonlinear network, what do you expect? Some nonlinear function of V1 and V2, so you can write I1 as some nonlinear function f of V1 comma V2 and I2 as some other nonlinear function g of V1 comma. Okay. So again, now since these equations are nonlinear, it becomes impossible to figure anything out. Okay. So however, please note the following. So basically what this means is that if I applied a battery of voltage V1 and applied a battery of voltage V2, the current flowing will be capital I1 and capital I2. Now, okay. Now the obvious question is, what happens when I change the voltage from V1 to V1 plus small v1 and this applied voltage from V2 to small V2 plus small v. What do you think will happen if V1 and V2 are again very, very small, where we'll again go and define what small means? What do you think will happen to I1 and I2? I1 will become I1 plus small I1, I2 will become I2 plus small I2. Okay? So in other words, I1 plus small I1 is f of V1 plus small v1, comma V2 plus small v2, but I1 itself was equal to f of V1 comma V2. Okay? Alright. From these equations, what do you get? So if V1 and V2, incremental V1 and incremental V2 are very small, how can you expand this? Can you expand this in a Taylor series? When we are talking about one port networks, we add a curve and we approximate the curve around a given point by the value at that point plus delta V or delta I times the slope at that point. Now you have a surface and you are approximating the value of this surface at a neighboring point by finding the value at that original point plus, earlier you would approximate a curve by a straight line. Now you approximate a surface by a plane. Okay. So Taylor series approximation will give you f of V1 comma V2 plus okay, so plus higher order terms in the series. Okay. So if you are just like analogous to the two terminal case, if you approximate it only by the first only the linear term, so to speak, then you can see that I1 plus small I1 is given by f of V1 V2 plus dou f by dou V1 times V1 plus dou f by dou V2 times V2. Okay. And what is f of V1 comma V2? So what does this mean? Small I1 is what? Dou f by dou v1 times small v1 plus dou f by dou v2 times small v2. By the same token, incremental current I2 will be dou G by dou V1 times V1 plus dou G by dou V2 times. Alright. So what do we notice? Even though the absolute voltage, absolute current I1 and the absolute current I2 are related in a nonlinear fashion, okay, to the absolute voltages V1 and V2, the incremental currents I1 and I2 can be linearly related to the incremental voltages V1 and V2. And just like in the one port case, okay, where the relationship between the incremental voltage and the incremental current depends on the operating point, okay, here also the relationship between the incremental currents and the incremental voltages depend on the operating point, now defined as V1 I1, V2 I2. Does that make sense? Okay. And there in a linear one port you only need one number. In a linear two port you need two numbers. In an incremental model for a one port, nonlinear one port, you need incremental model. There's only what? Once you find the operating point, there's only, given the operating point, there's only one number. The incremental model for a nonlinear two port requires four numbers. And what kind of matrix is this? I mean, it's a square matrix, yes, but what else? What linear matrix relates the currents to the voltages applied? Yeah, which is often also called the, if I1, I2 is blah blah, what letter do you use there? The admittance matrix, okay, or the Y matrix, okay. I equal to Y, the matrix of currents is Y times the matrix of the voltages. So this is now, and this is this a Y matrix, or is this, what do you qualify the Y matrix? Resistance, incremental resistance, Y matrix, incremental Y matrix. So now when you see a nonlinear two port, you find the operating points, compute the derivatives, you have an incremental model for the incremental